Okay, Hooke's law. Right, we're definitely dealing with springs here. And we're dealing with the difference between when springs don't have a weight on them and have varying weights on them. Okay, and what you'll probably noticed is the bigger the weight on a spring, the further this spring extends. So that's the extension with this first weight on it, and this is the extension with a larger weight on it. They're both extensions. And I think you should know that already. If you put more weight on a spring, it's going to stretch more, in effect. But we call those extensions. Often people get confused because they measure the original length of the spring, but that's not the case. We're just interested in the extensions, which would give the letter X. So, of course, with Hooke's law again, we need to bear in mind that we're dealing with weights here. Okay, you're putting a weight on it. So what you're saying is, as the force increases, so the extension increases, and that extension depends upon the spring. And the spring is characterized by this value K. So it's dependent on spring. Once again, bear in mind that because this force is a weight, you might be given an example where they say, oh, let's say, 500 grams is placed on this spring. What happens? Well, you first of all need to convert the mass into a weight, and then start thinking about our equation. Weight is measured in newtons. Extension is measured in, well, it could be centimeters, millimeters, meters. Often we keep meters as the primary use, and so therefore our spring, dependent on the spring, so it's called the spring constant, is given the unit newtons per meter. In other words, how many newtons are needed to stretch it by 1 meter? Let me give you some examples of that. Okay, so let's imagine we have, here's a spring, so we have an example. Let's say we have a spring which extends one centimeter for every 25 newtons of force. Okay, what happens if we put on, so let's imagine, so that's defining the spring, so what extension will be seen if we apply 50 newtons, 100 newtons, 200 newtons, or how about, let's look for 75 newtons. Okay, if you think you know, hit pause, and then otherwise I'm going to go through the solutions right now. Okay, so what happens if we had 50? Well, if we know that 25 newtons equals 1 centimetre, then surely 50 newtons must equal 2 centimetres. 100 newtons, because it's 4 times as much, would equal 4 centimetres. 200 newtons will equal, of course, 8 centimetres. So intuitively it's really easy to work out if you understand what that means. 25 newtons equals 1 centimetre. I think it's easier to look at it like that. However, we might want to look at it more mathematically, which suggests that the equation is asking weight equals spring constant times extension. And what we're looking for here, what extension will there be? We're looking for x. we rearrange it, that's W divided by K. Let me just place here as well. WKX here is our triangle for Hooke's law. Okay, now we've got that equation ready. We're asking now, let's look at the last one, 75 newtons. And let's substitute 75 in there. And the spring constant, I mean, effectively what the spring constant is in this instance is, we said 25 newtons per centimetre. So it's 25. So this is very simple. You get 3 centimetres is our extension. Now that you should have worked that out anyway, because if we know that 50 presents, sorry, if you know that 25 presents 1 centimetre, then you have 3 times that. So therefore you have 3 centimetres. But don't be afraid of using that equation, as long as you understand this idea that the spring constant is effectively saying how much force is needed to extend it by 1 centimetre. So therefore that's what this value of K is. It often confuses people. Okay, let's give another example. Right, let's have a, I want to know, right, we've got a spring of spring constant 10 newtons per metre this time. I'm going to change the units, see what happens. And I want to know what happens when we put on, so what happens, i.e. the extension when F is 30 newtons, 22 newtons, and 70 newtons. If you think you know the answer, hit pause, otherwise I will go through the answers right now. Okay, then here we go. First one. Well, when F is 30 newtons, well, let's first of all say our extension is the weight divided by the spring constant. In the first instance, we have 30 newtons, and our spring constant is 10 newtons per metre, so we have 3 metre extension. It's quite a considerable extension. In some ways, the spring constant is describing the stiffness of the spring. Okay, what about 22 newtons? Well, this one might not be as intuitive because it's not whole numbers, so actually the equation is very useful in this instance, but so that gives us 2.2 metres. And what about when it equals 70 newtons? Might give us 7 metre extension, quite a sizable extension. Okay then. Let's try another hit on this. So this is one last example, because it's quite mathematical. Okay, let's imagine we had a spring that extended 5 centimetres when 25 newtons was applied. What does K equal? What is the spring constant? If you think you know, hit pause, otherwise here we go. Here's the answer. Well, if I know that 25 newtons presented a 5 centimetre extension, then I can say that a 1 centimetre extension would have been used if there were 5 newtons. So therefore K is 5 newtons per centimetre. Or, if you like, we could do it mathematically, and we can say that here is my equation for Hooke's law. I'm looking for K, which is the force divided by the extension, and the force applied was 25 newtons, and the extension was 5 centimetres, giving me 5 newtons per centimetre. Now, if I want to be pedantic, I could change this into a different unit. I can say that 0.05 of a metre was produced. So therefore, what would have given a 1 metre extension? Can you see I'm moving from centimetres to metres here? So once you put that through, it should come out with 500 newtons will produce my 1 meter extension. Or if you like, F equals kx. My spring constant is force over extension, giving me 25 over 0.05, giving me 500 newtons per meter this time. Excellent. Okay, you'll probably be asked one last point, and that is to actually plot or to graph the Hooke's law. With Hooke's law, we always place the force on the x-axis, and be careful to write down your unit, and we always place the extension on the y-axis. Be careful to put your unit. I think we'll work on meters this time. Okay, the spring always behaves linearly or directly. It's got direct proportionality, which means it's a straight line through the origin, until a point. And at that point, suddenly it starts to deform. In other words, it means if you put the same amount of weight on, it will extend a lot more. This point is the elastic limit. It's the point at which it no longer obeys Hooke's law. This is still obeying Hooke's law in this region here, but no longer Hooke's law. In other words, in this region, F does equal kx. If you plotted another spring's behaviour and it came out to be lower than here, you would say this is a stiffer spring. And the reason why is because for the same amount of force applied, this spring has less extension. Similarly, this line here would be a weaker spring. Okay, right, I think that's it. That's a quick resume of the topic on forces. Good luck.